So in this lesson we will be using division to find factors of polynomials. It's not easy to always discover other factors of polynomials. One way we're going to learn today is to use long division of polynomials to factor, and also use a method called synthetic division of polynomials to factor. Let's just look at division with numbers first. Before we do anything with polynomials, let's look at how we divided numbers. Let's say we have number 24, and let's divide it both by 9 as well as 4, and let's write it out with some long division. So when I divided 24 divided by 9, I would get 2 with a remainder of 6, and I could write it as this: 2 plus 6/9, where 6 is my remainder. Now when I divided 24 by 4, in this case I get 6 and my remainder is 0. And so we would say that because the remainder is 0, 4 is a factor of 24, but in the other case 9 is not a factor of 24 because the remainder is not 0. So the same thing follows with polynomials. We could have a polynomial and we could check whether or not x minus 2 is a factor of f of x. What we would do is we would use division to find this out. We haven't divided polynomials before, so we're going to look at how we would divide a polynomial. And we would set it up in a similar way as we would set up long division, where in long division we take this number here and divide it by 9. We take a polynomial here and divide it by this x minus 2 factor which we're testing it against. So what we do is we start off by looking at this x cubed term and seeing how many times it would divide into x. So on the side here we can write this: x cubed divided by x, and we find it x squared. So we write x squared up top here, and then we take the x squared and multiply it times x minus 2, just as we took 2 here, multiplied it by 9 to get 18. We're going to take x squared, multiply it by x minus 2. And this is what we get. So the next step after this is we subtract. Just as again we subtracted 18 from 24, we subtract this polynomial from this polynomial. Then we continue. We have our 7x squared term right here. We divide it by x again to see how many times it goes into that, and it goes into it 7x times, so we write that up there. We then multiply the 7x times x minus 2 and put it down here, and then we subtract. We could do this one more time. We could take our 7x divided by x, which is 7. We put that up into the quotient area and multiply it. And then we get down to 16. Now 16 here, this is our remainder. We can't divide 16 divided by x, and so this is our remainder term. And in this case, our remainder is not equal to 0, and we could write it then as 16 divided by x minus 2, just like we wrote it as the remainder here, 6 divided by 9. And in this case, just like 9 is not a factor of 24, we will find here that x minus 2 is not a factor of this polynomial. So division is our method of determining whether or not we have x minus 2 being a factor of this other polynomial. Now let's just look at one more polynomial division. Let's look at a more complicated version, just because we haven't done a lot of polynomial division before. So say I have a polynomial divided by another polynomial, so I create this long division setup, And when I do this, make sure that you add any sort of extra missing terms. So like in this case over here, the numerator has an x to the fourth, x to the third, but no x to the 0 term explicitly written here. So when we write it out here, we add it. So we have the 4, 3, 2, 1 exponent terms of our x. And so we just go through the same method again as I described before. I start with the highest exponential term here divided by the highest exponential term in our divisor. And in this case I get 2x squared, so that's what I write up there. I multiply this by the divisor and I subtract, and I go through this again. I take my 3x cubed term divided by my x squared term, which is negative 3x. I put it into my quotient term up at top. I multiply it by my divisor, and again I subtract. I have one more step I can do. 8x squared divided by 8, or divided by x squared. That's equal to 8. I add the 8 term to my quotient term on top, and then I subtract one last time, and now I'm done, because 18x divided by x squared does not go into it, so this is my final remainder term right there. I have my quotient term on top, my remainder term on the bottom here, and I could write the whole thing as this division term here is equal to my quotient plus my remainder over my original divisor term here. So this is just another picture of polynomial division. The key idea was this: make sure that you add the 0x squared when there's a missing term here. Okay, let's get back to factoring. And factoring with other methods. We are going to look at a method called synthetic division, which is actually the method you used before. We called it previously synthetic substitution. It's the exact same method. We just have another name for it, a synonymous name for it. So suppose I want to divide this polynomial by x plus 3. So what I do is I take the opposite of x of 3 and put negative 3 here. So think of it as x minus negative 3. We put that term right there, and then we take our coefficients of our polynomial here in our numerator and put it across here. So again, this is just the synthetic substitution step that we learned before. We bring the 2 down and we multiply it times negative 3. We add 1 plus negative 6. We multiply that by negative 3. We add negative 8 and 15. And then we get 7 multiplied times negative 3. And then we add these together and we get negative 16. And these terms, the nice thing about these terms here is that these are the actual coefficients of our quotient term. So the 2 becomes x squared, 2x squared, and why x squared? Because it's one less, or 1 power less than our x cubed term that we started out with up here. So we started out with 2x cubed. This was our x cubed term. And so this 2 here represents the coefficient in front of the x squared term. And then so on and so forth. The negative 5 is the coefficient for our x term. And then we have our plus 7. And then the remainder is negative 16 in this case. Negative 16 over x plus 3. So this is how synthetic division works, and it's a very quick way to divide. And you'll see here that this is why synthetic division is so nice, because it's a lot easier to do this than the long division that you saw on the previous slides. So in this case, we have a remainder here, and we say again that since this remainder is not equal to 0, then we could say that x plus 3 is not a factor of the polynomial up here. Now you remember that we used synthetic substitution to evaluate f of x at -3. F of -3 we found was -16. That's how we did it before when we were using synthetic substitution. We substituted -3 into this to find out our solution of the function. So we actually have this theorem, which we call the remainder theorem, that says just this, that if we have a function and we divide it by x minus k, the remainder right here is actually f of k. So we have f of -3 here. When we evaluate it here, we get 16. The remainder is f of -3. That's what we were finding before with our synthetic substitution. So now we just have a theorem that gives the foundation for that. We have this factor theorem that says this: a polynomial f of x has a factor x minus k if and only if f of k equals 0. What does this mean? Let's look at it graphically. I think that's the easiest way to understand this. If we have a polynomial and it has, this kind of bumpy form here, if x minus k is a factor, then it means that we have this point k where f of k is equal to 0. Basically, it's saying it crosses the x-intercept right at k. That's what it means for us to have a factor. So these are three synonymous statements. K is a 0, x minus k is a factor, f of k is equal to 0. These are all saying the exact same thing. And we actually saw this before with the intercept form. If we had x minus k as if you remember the intercept form of our quadratic, it meant that k was an x-intercept. And so again, these are synonymous terms. They mean if somebody tells you that k is a 0, you also know that x minus k is a factor. Okay, let's look at two more examples. So again, let's do this problem where we're asked, is x minus 4 a factor of this polynomial? And if so, factor it completely. So the way we approach this is by setting up synthetic substitution or synthetic division, because it allows us to quickly divide. So we take x minus 4, we take the 4 and bring it right on down here. We take each of the coefficients of the polynomial here and put it here. And since there was x to the third, x to the second, x to the first term, we did not need to add any extra zeros into here. We then go through our synthetic division and we get the following. Our remainder is 0, so indeed it is a factor, just like it was, so it is a factor because our remainder is 0. F of 4 is equal to 0, and by the factor theorem, we say that x minus 4 is a factor. Going further here, we know that these are the coefficients of our quotient, so we can quickly write down our quotient term, where we have x squared minus 2x minus 3. Again, the x squared is one less power from the x to the third, and then we have the next term and the next term subsequent. So we know that x minus 4 is a factor, and then we have this also as the quotient term, which we can continue to factor. In this case, we can just use our factoring methods we learned in the past, and we can factor it down to x minus 3 times x plus 1 as well. So this is how we would factor this polynomial completely, given some initial information that perhaps x minus 4 is a factor. So our last example, let's look at a case where we're given an equation. We're given some information that when x is equal to 1, p is equal to 25. And we can indeed plug that in and find that p is 25. But the problem goes on and says, find other x's when p is 25. So the way we would set that up is by plugging in 25 into the equation. And you might be tempted to also plug in the 1, but you don't want to do that because if you plug in the 1 into this, you will lose all of your variables and there will be nothing to solve. So you want to find other x's when p is 25. So we write this equation and then we rewrite it where we move the 25 to the other side and simplify it into a standard form. Since we're given the fact that x is a 0, or x is equal to 1 is a 0, or x solves this solution, and then if we plug x minus 1 in here, it's equal to 0. We know that x is equal to 0. X equal to 1 is a 0. Therefore, x minus 1 is also a factor. Then we can use our division again, our synthetic division. And in this case, we take our coefficients 21. And I had to add a 0 here because there's no x squared term here. I bring the negative 46 down. I bring the 25 down. And then I go through my synthetic division procedure. And I see I get a remainder of 0, which is good because I knew already ahead of time that it was a factor, so that's what I expect. If I don't get it, I'd have to go back and check that. Now from here, I get my coefficients of my quotient term. And then from here, I try to factor it, but I can't factor it, so I end up using the quadratic formula to find other x's that solve this equation. So I just plug in my b, negative b plus or minus b squared minus 4ac divided by 2a, and I solve to find other x's could be negative 1.7 or 0.7. So this concludes the lesson. Again, the big idea is this. We can use synthetic division to test whether or not a term is a factor or not. And if it is a factor, the remainder will be 0. And we can even then use the results of our synthetic division to find out the coefficients of the quotient term and further factor. Okay, have a good day.